Hi, I'm Jayant from group number 32, and here are my teammates Mustafa and Chris. What we're doing is a movie box office revenue predictor from 2015 until November the 5th, 2023. The objective of our project is that we're trying to figure out how much a movie can make given its other features. So this is a prediction problem. So we're doing regression, and it is a supervised learning problem because we have training examples which are labeled. And since the data set is static, we have a batch learning problem. And the practical use is that say you're a movie maker and you want to know if how much your movie will make. So you can use our product to get an idea of how much your movie will make money. Looking at the dataset for the first time, we notice that there are 20 features in the dataset, including the target value, and other features include stuff such as keywords, title, ID, genre, etc. We notice that between the correlation of features, ID obviously does not correlate well with the revenue, but budget does, and we get a good insight from this for the data cleaning. Moving on to the pre-processing, we realized that there was a huge challenge up ahead because the data was extremely skewed. There were about 75% of values for revenue put in as zero, so the dataset was not ideal, and this challenge was giving us a huge headache. And to remedy this, we resampled this dataset to have the number of zero quantities as equal to the number of non-zero quantities, and the number of zero instances we chose them randomly to ensure that we're not meddling too much with the data, and the predictions are accordingly. Thanks to that resampling, our plots for runtime versus revenue got a lot better, like over here. And then we put a threshold on it because 75% of the movies were no longer than 90 minutes. So we put a threshold on 150. Continuing with this data cleaning, we noticed that in this table, about 70% of the recommendations are missing data, and then for 49% of the keywords are missing, and also credits, status, ID, title, they don't matter to the revenue. So we dropped all these in the red. So another challenge that we came across was that genres were making over 3,000 categorical features. The problem was that genre was originally a string data type and we could not analyze it, so we had to convert it into a list. And from that, we had to convert one hot encode it and make it a table like this. So moving on to the pipeline, we had a simple imputer for both the numerical and categorical data, as you can see over here. And it was doing mean for the numerical values and mode for the categorical data. Then we had a standard scaler for the numeric data and one hot encoder to convert categorical data into numeric values.
For our model, we used a linear regression, an XGB regressor, and a rigid model. Linear regression is a statistic model used for modeling the relationship in between a dependent variable and one or more independent variables by filtering in a linear equation with the observation data. The goal of linear regression is to find the values of m and b and minimize the difference between the observed values of y and the values predicted by the linear equation. This is often done using the method of least squares, where the sum of the square difference between the observed and predicted value is minimized. The XGB regressor is a regression-based model on the XGBoost algorithm. XGBoost is a assembly learning method that builds a decision tree sequentially to correct errors. The key features include regularization, handling missing values, optimization through gradient descent. The XGB regression is tailored to predict continuous numerical values using the mean square error objective function. It's efficient, scalable, and provides a feature importance score for understanding the behavior model. Ridge regression is a linear regression model that adds regularization to prevent overfitting. It introduces a penalty term that to a traditional linear regression objective controlled by a hyperparameter. This term helps shrinks the coefficient towards zero, making the model more robust and suitable for situations for the predictor. These weren't the only models we tried. We also attempted the random forest regression and polynomial regression. Both of them we didn't go through with due to the same issue where, due to how large the dataset was and how many features it had, it took far too much memory to use in the pre-processing. Last we checked, it was in the multiple of terabytes. If we had more time to fine tune our data set, maybe we could have experimented more with these models, but in the end, we didn't have enough time and we decided to cut them out.
Let's talk about our results. So when it comes to linear regression, it ended up doing the worst, and I'll explain why in the next slide. For XGB and ridge regression, they ended up doing very well compared to linear regression at the very least, and I'll explain why as well. And the reasons the values are relatively large is because the revenues, first of all, there's a lot of variance, and secondly, the revenues are very large for a lot of these movies. So let's look into it. The reason linear regression did so bad was because the linear regression we were using had no regularization, and our variance for our values, or our standard deviation for our values, was very high. So as a result, it performed poorly. Now let's explain why XGBoost did better than ridge regression. First of all, XGBoost deals with outliers much better than the other two models, and secondly, it can model more complex relationships between features that aren't linear. So we could have a polynomial model, we could have an exponential model potentially with XGBoost. Now let's analyze the graphs for our XGBoost model. So for the scatter plot, as we can see, there's definitely a linear relationship between the revenue predicted and the actual revenue, which is a very positive sign. For our bar graphs, as we can see, many of the bars line up, as we can see by the overlap. So something that I personally noticed was that for edge cases, like really very large values and very small values, our model had difficulty picking up on that. But generally, our model predicted the actual revenue versus the predicted revenue relatively well. Finally, for our violin plot, as we can see, the range of values that we have for our predicted revenue is a lot higher versus the range of values for the actual, and our model tends to lean more towards higher values, so it ends up predicting larger values than necessary. Now let's talk about the limitations that we faced with this project. First of all, I'd like to talk about our dataset. Our dataset was lacking in much of the target features. Over 75% of our revenue features were missing values. They were all zeros. And we remedied this by resampling, but obviously it would be even better to have actual revenue values to predict more effectively. Secondly, a lot of our data was very useful, but we need to re-engineer it in a very complex way, such as the actors would be very relevant in the keywords, as well as the production company. Finally, there's a lot of features that could have been in this dataset that would have made our model extremely precise, such as the amount of money spent on advertising, the country it was originally released in, the movie was, and the original rating of the movie. All of these would have only contributed to the precision of our model. Thank you for listening to our presentation, and I hope you have a good remainder of your day.